Okay, I'm going to get started. Last class we introduced the field equation for magnetic forces arising on moving charges due to magnetic fields. Today's class is going to focus on applications of the field equation, examples of the field equation. So that's the plan. I want to go through these 4 bullets. I'll show you a couple of problems, couple of examples involving the field equation for a single moving charge. So that'll be the first part of the class. I'll then show you the field equation, an alternative version of the field equation for not a single moving charge, but a electrical current, a collection, a flow of charge. Then we'll look at a particular example of the magnetic force on a current carrying wire, straight wire, via the field equation. And then we'll look at a particular case of the magnetic torque on a current carrying loop. Again, an application of the field equation. So the whole class is about the field equation that we introduced last class. We're going to be talking about the right-hand rule again that we introduced in this class. So it's a lot of problems, a lot of examples in today's class. Okay, we all love the Earth. We're not going anywhere else. This first problem that I want to work through, is an example of the Earth, in that the Earth, that's interesting because it's massive, it exerts gravitational forces. It's also electric, it's charged and exerts electric forces. And we've said it's, in the last class, it's also magnetic. It exerts magnetic forces. And in the first example, we're going to use the field equations for electric, magnetic, gravitational forces and just compare the electric, magnetic, and gravitational forces on a charge, on an electron, due to the Earth. And we're going to be using the field equation. Okay, so here's the example. And this example, as I say, involves thinking about the Earth as having mass, having charge, being a magnet, and therefore having a gravitational field that you met in 211, having electric and magnetic fields that you're meeting in 213. And we're told in this particular problem that at the equator, or near the equator, the Earth's magnetic field is about 50 microtesla. So that's the strength of the Earth's magnetic field near the equator. We're told that the Earth's electrical field near the Earth's surface at the equator is about 100 newtons per coulomb. And we already know the gravitational field, or gravitational acceleration of the surface of the Earth. That's 9.8 meters per second squared. What I just told you in that list of 50 microtesla, 100 newtons per coulomb, 9.8 meters per second squared, is the magnetic, electric, and gravitational fields at this location. Those are all fields that convey forces, conveying the magnetic, electric, and gravitational forces. So we're going to take those fields where we're told the values of the fields, and we're going to calculate the corresponding forces on a charged particle. This is on an electron moving at a certain speed in the neighborhood of the Earth. And so we're going to take these fields and we're going to calculate the gravitational, magnetic, electric forces on an electron that we're told has a speed that is 6 million meters per second and is traveling eastward. So that's our plan. I made a sketch of the problem here. I think I made it, with the sketch, made it look more complicated than it actually is. On the sketch, I'm sketching a few things, but before I describe the things on the sketch, let me explain my perspective as I drew the sketch. I had to imagine that I was standing at the equator. And so I imagined going to the equator, and I remembered, for some reason, from geography class 50 years ago, that Ecuador is on, why it's called Ecuador is because it's on the equator. So I imagine going to Ecuador and being on the equator. Ecuador's somewhere here. And I imagine looking out over the Pacific Ocean, right? And that was going to be my perspective on this problem. I'm at the equation, I'm in Ecuador, I'm looking out over the Pacific. If I do that in my sketch, so in my sketch, north is to the right as I look out over the Pacific. So this is the north direction. East would be behind me. If I'm looking out over the Pacific, I'm looking west. And so that's the orientation of this picture. This picture is drawn as if I'm in Ecuador looking out over the Pacific. And then I've drawn the three fields that I've been told. I've been told the magnetic field is 50 microtesla. I pictured it in green. And remember, we're told that it's pointing towards the north. And so I pictured it as heading towards the right because that's the north in this perspective. I sketched in blue the electrical field. The electrical field is easy to sketch, straight downwards. So I've sketched that as these blue lines field lines heading downwards. And then I've got the gravitational field. We don't normally draw the gravitational field. We kind of just write G. But here's my gravitational field. It's also downwards. This is responsible for the attraction of the Earth. And so I've drawn those three fields in green, in blue, in red, and now I've added to the picture the electron and the motion of the electron, and so that's in gray here. Here's the electron. If the electron is traveling eastward, that's opposite the direction. Remember, I'm looking over the Pacific at the water, and I'm looking in the westerly direction. So the electron, if it's traveling eastward, is coming out of the screen in this picture. And that electron has 6 million meters per second speed. It has a charge, that's the electronic charge. It has a mass, which is the mass of the electron, about 10 to the minus 30 kilograms, this tiny mass. And so this is all the information I've collected together on this one picture for all of these fields that I'm going to calculate, all of these forces on this particular electron traveling with this particular speed, in this particular direction. And so that's the plan. So let's see if I can do this. I guess I'll do it on the document camera. And so here I've started it out, okay? And actually I think this is a better diagram. It has less of the field lines on it. It just has one sample field line for all the three fields, and it has this size of the three fields that carry the electric, magnetic, and gravitational forces. Right, so we want to calculate these three forces. Let's start with gravity because we love that. Gravitational force. What's the field equation for the gravitational force? Field equations are the product of the property that experiences the force and the field that carries the force. The property that experiences the gravitational force is mass. The field is, as we said, G. That's the gravitational field, the familiar 9.8 meters per second squared. So F equals mg, that you know well from 211, is a field equation for the gravitational field. We know all the numbers in this field equation, right? We know the mass of the electron is 9.1 times 10 to the minus 31 kilograms. We know the acceleration of gravity, I've also written that down, it's 9.8 meters per second squared. And so I've only got to multiply those two numbers. And as I never do, because it takes me too long on the document camera. I won't write the two numbers in, but I will write the product. The product I got is about 8.9 times 10 to the minus 30 newtons. And so that's the force. And that force, that's the size of the force. That force, as we know, right? We're pulled down towards the Earth. Everything's pulled down towards the Earth by the attractive gravitational force of the Earth. The electron is also pulled down. So this is down. Well, that was easy. Let's do electricity next, because we met that before magnetism in this class. So we're going to figure out, I'll figure out again the size of the electrical force, and then we'll compute then we'll figure out the direction. Again, we want the field equation. The field equation is the property that experiences the force times the field that carries the force. For the electric force, that's just the equivalent of mg is QE. So Q is the charge, that's what feels force. E is the electrical field, that's what carries force. So we just got to multiply those, and I've already written those two numbers down too. The electrical charge is the electronic charge, 1.6 times 10 to the minus 19 coulombs. The electrical field is 100 newtons per coulomb, so I just got to multiply the electronic charge by 100 newtons per coulomb. I'm working out the size here. I won't worry about the sign, so maybe let me put just worrying about the magnitude of the charge. If I multiply these two numbers, I got 1.6 times 10 to the minus 17. And of course, that's also newtons. And what direction is that? So a bit more subtle here. The field is down. If this was a positive charge, the force would also be down in the same direction as the field. But this is a negative charge, so we're remembering that for a negative charge, the force is opposite the field. So this is, if the field is down, the force will be up. One more to go, the new one, the magnetic force. So we've got to figure out the magnetic force, F. We put a subscript B on it often because we call the field the B field. Don't know why. Anyway, we've got to use the field equation again here. Again, it's the property that feels the force times the field that carries the force. The property that feels the force is moving charge, so I'm going to write QV. Got to multiply it by the field, that's B, and then there was this subtlety that moving charge has a direction, B field has a direction. There's a sine theta for the relative direction of these two directional quantities, the motion and the field. So there's a sine theta that you don't see in the gravitational field equation or the electric field equation. Now just got to multiply all these things together. Now, one point is that in our particular case here, what's that angle theta? Well, the magnetic field is towards the right in my sketch here, so it's towards the north. The particle is moving out of the screen here, and so they're at right angles. There's 90 degrees between the two directions, V and B here, and so theta is 90 degrees, sine theta is 1. So that's easy, and I just indicated that there. Then we just got to multiply Q, which we've written down. We've got to multiply V, 6 millimeters per second, that we've written down. We've got to multiply B, that we've already written down. It's 50 microteslas, 5 times 10 to the minus 5 teslas. I'm not going to write all those numbers in. It'll take me 5 minutes, 10 minutes. I've already figured it out. If I multiply all those numbers together, 4.8 times 10 to the minus 17 newtons. That's the size. I didn't worry about the direction. I just thought about the size of the charge, for example. If I want the direction, you'd be pleased to know I need the right-hand rule. I got to use my right hand, I'm going to point the palm of my right hand in the direction of the velocity vector. The velocity vector is out of the screen. I'm going to curl my fingers in the direction of the magnetic field. So the magnetic field is going, I'm looking at this screen, but I've got to do it according to this. The this is extremely, I just made the right hand roll is already confusing, but try doing the right hand roll in a mirror is basically what I'm trying to do. So let's not do that. The electron is going towards you, out of the screen. The magnetic field is going towards the right, that we call the north over here. So I'm curling my fingers towards the right. My thumb then points in the direction of the force on a positive charged particle, like a proton, but this is not a positive charged particle, it's an electron, it's negatively charged, and so the force is downwards. So this is down. Interesting thing, right? Interesting thing when we compared these three forces based on the three fields that are created by the Earth's properties, its mass, its charge, and its magnetism. We think in our everyday lives, right, we think of the Earth's effect on us as being gravity, right? Gravity overwhelms Earth's electrical magnetic effects on us. So we live in a gravitational world. But this little old electron, actually lives in what is dominantly a magnetic world. As far as the electron is concerned, it doesn't see the Earth's mass at all. And it mainly feels, experiences the Earth's magnetism. So it's important to remember that we have a particular perspective on the Earth, and we think the Earth as a mass, but the electron here has a very different perspective on the Earth. It would experience the Earth as a magnet, mostly as a magnet. You might wonder why on the original slide I put a picture of a bee. If you spotted the bee in the top left-hand corner of the original slide. I put the bee there because bees are another interesting case. They kind of live in an electrical world, not like the magnetic world of the electron for the Earth, not like the gravitational world for us and the Earth, but they live in a more electrical world because remember you could charge things by rubbing the glass rod with silk or the plastic rod with cat's fur. Well, bees are charging themselves all the time. They're flapping their little wings and they're charging themselves up, and they interact electrically with the Earth. So they live in a very different world too from an electron, which lives in this kind of magnetic world, from us, lives in a gravitational world. They live in a much more electrical world in their interactions with the Earth. Okay. Wanted to talk about another motion of a charged particle. This is circular motion of charged particles. This is a beautiful type of motion that's exhibited by charged particles in uniform magnetic fields. Now, we know circular motion from 211, like the planets move in approximate circular motion around the Earth. And that's due to the gravitational force. Well, also, in the case of magnetism, particles like electrons or protons or, ions of some type will execute beautiful circular motion in a magnetic field. So I just want to talk about that a little bit. This picture here shows you the circular motion of electrons in a magnetic field. So in this picture here, there's a magnetic field, a uniform magnetic field that's into the screen. So you have to imagine all these field lines of magnetism heading in towards the screen. So this is a region of magnetic field, and in this region of magnetic field is what we call an electron gun that fires electrons into that region of magnetic field. So here's an electron gun, and here's a stream of electrons emerging from that gun. And we can see I mean, you can't normally see an electron, but we can see an electron here because these electrons are actually fluorescing some gas that's filling the space of the magnetic field. And these electrons, as they move through that gas, fluoresce that gas, light up that gas, and you can see the tracks of the trail of the electrons. And you see them through this band here. They're executing this near perfect circular motion. And charged particles in a uniform magnetic field, in a perpendicular uniform magnetic field, will execute this perfect circular motion. It's kind of the magnetic equivalent of orbital motion, but it's with magnetism rather than planets and the sun and the gravitational orbits. There's a very special feature of particle orbits in magnetic fields. And that very special feature of particle orbits in magnetic fields has to do with the period of the orbits, or the kind of the frequency or the angular frequency of the orbits. Those are, how many orbits per second or how many radians per second. With the case of the planetary orbits around the sun, for example, you might remember from 211, if you've got a good memory, a thing called Kepler's laws. And that was a prescription that told you how the period of the orbits, so the length of a planet's year, depended on the radius of the orbit. So it tells you the relationship between our distance from the sun on the Earth and the Earth's length for a year, that is 365 days, for example. So that's a Kepler's law for gravity. For magnetism, there's kind of an equivalent of Kepler's law, and it's a very interesting case that actually this omega here is the angular frequency of the rotational motion. That's radians per second. It's 2 pi times the frequency f of the rotational motion, which is the frequency of the complete oscillations per second. And that angular frequency, or regular frequency here, f, just depends on the magnetic field, so it depends on the strength of the magnetic field. Obviously, if there was no magnetic field, there would be no rotation. If there is a magnetic field, there is the circular motion. The larger the magnetic field, the faster the magnetic rotation, the faster the orbits. It's just the magnetic field times Q over m. Q is a characteristic of the particle executing the circular motion. It's just its charge. Mass is the other characteristic of the particle that's executing the circular motion. So it's just its mass. An electron is a particular particle. If you want to think, well, what is an electron? It's just a packet that has a certain charge and has a certain mass. What is a proton? It's just a packet that has a certain charge and has a certain mass. So all particles of nature have characteristic masses and charges. That's their personality, basically. And this Kepler's law says that the speed at which they go around, the frequency at which they go around in circular motion, or the period of their circular motion, just depends on their charge to mass ratio and the field that you've immersed them in. So no matter whether they're going in big circles or small circles, no matter whether they're going fast circular motion or slow circular motion, the period of their circular motion, the frequency of it, is always just dependent on Q over m, the charge to mass ratio. And so that's an amazing feature of magnetic orbits. It's not true of gravitational orbits. I want to show you where that comes from, and then show you an example of a calculation involving it. I'm going to go through this pretty quickly because I really want to get onto the example problem. But here's a charged particle in a magnetic field. The magnetic field is going into the screen. Remember, the code for field into the screen is the cross, is the code for field coming out of the screen is the dot. So this is a field in green that's going into the screen. Here's our charged particle, positive charged particle. When it's moving towards the right here in a magnetic field. This is an example right-hand rule. So this is why I'm showing this. When it's moving towards the right, what's the direction of the force in this magnetic field? So let's all think about this. Well, the motion is towards the right, so I would, if I want to visualize it, I'm going to point my palm of my right hand towards the right. The magnetic field is into the, so I've got to do this in the orientation of the picture. The magnetic field is into the screen. So I'm going to point my fingers into the screen. My hand is pointing towards the right, that's the velocity vector. My finger's pointing towards the screen. My thumb is pointing up, that's the direction of the force. So at the moment, that charged particle is downstairs here. There's a magnetic force upwards on it. So it's obviously going to start curving upwards. Let's catch it a moment later when it's up here. It's been deflected up here. Let's think again. We want to really practice the right-hand rule. I'm going to drive it home. Let's think about the right-hand rule for the particle at this location here. The particle's going up. So I'm going to point the palm of my right hand up. The magnetic field is into the screen still, this uniform field. So I'm going to curl my fingers in towards the screen. Now look at my right hand. My thumb of my right hand is now, it's not pointing upwards anymore. Now it's pointing towards the left. And so not only has the velocity vector of the particle changed, because the velocity vector has changed because of the deflection and the magnetic force, now the force direction has also changed in correspondence with the change of the velocity vector. We could walk around this whole circle. I could spend the rest of the class walking around the whole circle doing right-hand rules, but I won't. If we did that, we'd discover that as we walk around the circle, the force always points towards the center of the circle. That magnetic force is providing a centripetal force that causes a circular motion. That's why you get magnetic orbits. Let's run with that. So this is the idea that we got out of the picture. Magnetic force FB is supplying a centripetal force, we call it FC. Let's equate our equations for the magnetic force and the centripetal force. Set magnetic force equals centripetal force. That's what I did in this line here. Magnetic force is QVB here. I didn't write down the sine theta because it's sine of 90 degrees, which is 1. The 90 degrees is because the magnetic field and the velocity vectors are always perpendicular to one another in this picture. The field is into the screen. The velocity is always in the plane of the screen. So they're always, no matter where the particle is, at right angles. So this magnetic field is QVB. If you remember, you've got a better memory than me. Back to 211. What is centripetal force? It's the force you need to execute circular motion. It depends on how fast you want to execute the circular motion, the radius of the circular motion, and the mass of the particle executing the circular motion is mv squared over r. So just plugged in these. If you rearrange this equation, right, now it's just basic algebra from kindergarten or wherever we learn it. If I rearrange this equation here, firstly I'm going to calculate, there's an excess of v's. There's a v squared on the left and a v on the right, so I can at least cancel out a v on the left and right. If I do that and then rearrange for the velocity of the circular motion, I find that the velocity of the circular motion, v, depends on this characteristic, this personality of the particle, what we call the charge to mass ratio, multiplied by the magnetic field that's causing the circular motion, and is in proportion to the radius of the circular motion. So you discover, this is quite unlike gravitational orbits, where the relationship between the radius of the orbit and the speed of the orbit is more complicated. For magnetic orbits, the relation between the speed of the orbit and the radius of the orbit is very simple. the speed of the orbit is simply in proportion to the radius of the orbit. If you double the radius of the orbit, make it twice as big, you're going to double the speed around the orbit. That is an enormous consequence. This is this fantastic consequence about magnetic circular motion, is that if you think about not the speed around the circular orbit, but the number of orbits per second, the frequency, or the number of radians per second, the angular frequency, or the period, how long to go round, all those things, the frequency f, the angular frequency omega, the period t, they all just depend on the charge to mass ratio of the particle and the magnetic field. They don't care whether it's a big old orbit and a fast-going particle, or it's a little orbit and a slow-going particle. Always the period of the orbit, the length of kind of the magnetic year, the frequency, angular or regular frequency, omega or f, they just depend on the characteristics, personality, the charge to mass ratio of the particle. So it's a really interesting thing. Okay, let's apply that understanding to a particular problem. Actually, this problem involves a little bit of electricity and a little bit of magnetism. We'll skip through the electricity bit pretty quickly because we're really, this group of lectures up to test 2 is focused on magnetism. We're told that we're using a mass spectrometer. Mass spectrometer is a device that can allow you to measure the masses of particles. And you measure the masses of the particles by measuring ultimately the radius of the curvature of the particles. We're going to measure we're going to think about a charged particle that has 1 unit of electronic charge. It has a mass of 2.3 times 10 to the minus 26 kilograms. I picked that because that's carbon-14 mass, which is used in carbon dating, which is one reason that you use mass spectrometers. But that's needless background. Here's the mass. We're told that we're going to accelerate this charged particle in by a potential difference of 250 volts. We're going to then deflect it in a 0.5 Tesla magnetic field, and we've got to calculate the radius of the magnetic orbit of this carbon-14 particle with this particular charge to mass ratio. So that's the problem. We're told the accelerating electrical field. We're told the orbital causing magnetic field. And from those pieces of information and the personality of the particle, the personality of this carbon-14 ion is that it has electronic charge and the mass of carbon-14. We're going to use that information to find the size of the orbit. Okay, maybe I'll do this on the document camera. Here we are. I started drawing this one too, and filling in the numbers I know. That word problem, right? You can, if you digest the awful writing, you can digest it into it's telling you some information on the electric part of the problem, the potential difference. On the magnetic part of the problem, the magnetic field, so 250 volts, half a Tesla, and it's telling you about the particle. It told us the charge and mass, and therefore, if we needed the charge to mass ratio of the particle. So that's the information that is given. I want to figure out the radius of the particle in the magnetic field. So that's this region here. That's what I want to figure out. But actually, to do that, I'm going to need to know the speed of the particle. The speed of the particle that was accelerated by this electrical potential hill here. So to find R, I've got to first find, I'll just write it as a little v here. I've got to find that velocity or that speed here. And so there's really 2 parts of this problem. I'm going to use my test 1 knowledge of electricity to find the speed, and then I'm going to use my test 2 knowledge of magnetic field equation to find the radius of the orbit. So let's go ahead and do that. I'm going to write down my starting point for finding the speed. Unfortunately, I've got little v's and big V's here, which is going to be potentially confusing. We've got a big V, which is the voltage that the charged particle is accelerated across as it rolls down a potential hill. We've got a little v, which is the speed. To find the speed, the little v, from the voltage, I'm going to use energy conservation. And the idea is that when you accelerate this charged particle down an electrical potential hill, you're turning electrical energy into kinetic energy. This is just a transform of energy. The electrical energy is QV. Remember that equation? So that's the electrical energy. This particle is starting at the top of the hill. It's going to roll down. Starts with potential energy of QV. It rolls down the potential hill. It loses that energy, but it acquires a corresponding amount of kinetic energy that's 1/2 mv squared. And so equating the initial potential energy and final kinetic energy, I get this little equation here. Now this is perfect. This is perfect for me because I can rearrange this. I want that speed that we called little v, and if I rearrange it, I get 2q big V, the potential, divided by m square root of that, because we had a v squared in the kinetic energy. So that's my little bit of kindergarten algebra. And if we look at the right-hand side there, look at the right-hand side. Think about it. Do we know these numbers? Well, yeah, we do. We know the 250 volt potential, and we know the charge and the mass of this carbon-14 ion, and so we can just plug in those numbers and we'll get a speed. And so I already did that, of course. And I got 5.9 times 10 to the 4 meters per second. So this is 59,000 meters per second that carbon-14 ion has acquired by sliding down this electric potential hill. Okay, now we've got the speed. Let's find the the radius of the orbit. We can find this radius here. Remember the equation from my introduction to this beautiful circular motion, that the speed was in proportion to the radius of the orbit. It depended on the magnetic field B. It got faster with a stronger magnetic field, and it depended on the personality of the particle, its charge to mass ratio. It's this little equation here. So I just took this from my introduction on the last slide. We want the radius though. So we've got to rearrange it. If we rearrange it, we've got m over q rather than q over m, but it's still the characteristics of the particle, divided by qb. Again, every number here I know. I know the speed is 59,000 meters per second. I know the mass and the charge of the carbon-14 atom because we were told those, and I know the magnetic field. It was 1/2 Tesla. So I plug in all those numbers, and if you do that, I got it was 0.017 meters. It's 1.7 centimeters, and so that's the radius of the circular motion. Anyway, that's an example, an illustration of putting together some of the stuff we learned in electricity, some of the stuff we learned in magnetism, for what is, things like carbon-14 data and mass spectrometry are extremely important. And this is how mass spectrometer works. This is how you can measure masses of particles, charges of particles, properties of particles with a mass spectrometer. Okay, want to talk about an alternate version of the field equation for magnetic forces. So we've been talking about the field equation for magnetic forces. We've been talking about QVB sine theta. But there's actually an alternate version for the field equation on moving charged particles. The reason there's a useful alternative is sometimes you're dealing with a single charge that's moving in a magnetic field, so you'd use QVB sine theta. Sometimes you're dealing with an electrical current in a magnetic field. Now, electrical current is a collection, an assembly of moving charges in a magnetic field. So an electrical current will obviously experience, like a single charge, a magnetic force in a magnetic field. And so there's a field equation that involves the language of current rather than involves the language of velocity. And so we're just going to introduce that, and then we're going to go ahead and use that. That's what I just said. This slide just introduces this new alternate version of field equation for magnetism and compares it to the old familiar field equation for magnetism. So QVB sine theta is the old field equation. Remember, it relates the property of the property that experiences magnetic forces and the field that carries the magnetic force to the magnetic force itself. Here's the new version of it. It involves the property that experiences a magnetic force from its current flowing down a wire. So it involves the current and the length of the wire. And then it also involves, like before, the magnetic field that's conveying the force, and together their product is going to determine the magnetic force itself. And so I'm saying here that there's two versions of the field equation. At their heart, at their core, they're really the same, but one involves just a single moving charge. The other is a collection, an ensemble of moving charges. We're just using a bit different language for the description of the single charge versus the collection of charges. We're using QV for the single charge, IL, current times length of the wire, for the moving charge, so for the electrical current. So that's all there is to that. There's just two versions of the field equation. Just wanted to point out this little bullet here. If you think about QV and IL, these two alternate ways of describing the property that experiences magnetic forces, they both have directions, right? It's important they both have directions because the magnetic force depends on the directions of the charges. The current has a direction, obviously, along a wire in one or other direction, and the velocity has a direction. So they both have that important ingredient of direction. They both obviously better have the same units. They both better have the same units because they're going to be multiplied by the magnetic field to create the magnetic force. And indeed, if you work it out, they do. The units of QV is easy to see. It's coulombs per meters per second. Sorry, it's coulombs meters per second. It's the units of charge times velocity. But actually, the units of IL are also coulombs meters per second. So just, they have the same units. Okay. The right-hand rule that we've been applying to single moving charge particles in a magnetic field, we can also apply that to electrical currents that are immersed in a magnetic field. And we just apply it in the same way. So that right-hand rule where we had velocity for the palm of the hand, we pointed our fingers in the direction of the magnetic field, and our thumb was pointing in the direction of the magnetic force. That all applies to the case of a current versus a single moving charge, except the palm of the hand in the direction of the velocity of the single charge. It's now the palm in the hand in the direction of the current, the conventional current that positive charge carriers would move it. So that's how we're going to use the palm of the hand. Just to show you an example on this sketch here, I tried to sketch a current that's flowing left to right in red here, a field that's going in towards the screen in green there. What's the direction of the force on that current carrying wire? Was the right hand rule again. We're going to take the palm of our right hand, we're going to point it in the direction of the current rather than the velocity. We're going to curl our fingers in the direction of the field. They're into the screen. My thumb is pointing upwards. That's the direction of the force on that conventional current. And so just the same application, but changing the language of velocity to current. Let's look at a couple of examples of this. We're going to look at the case of a straight wire, and then we're going to put a few straight wires together to make a little rectangular looper wire, and we'll look at that case. And we're going to be thinking about what are the forces that arise on the straight wire and the looper wire, what are the torques that arise on the wires. So this slide and the next slide are just thinking about the direction of the force on a straight wire. Again, this is the purpose of this, really just keep practicing with the right hand rule. In this particular picture here, I've got a wire marked here. It's immersed in a magnetic field with these crosses here. Remember, the crosses mean the field's going into the screen. Dots would mean the field's coming out of the screen. And we're asked to figure out the magnetic force, and hence the kind of magnetic deflection of this wire in this region of magnetic field. So what we're being told is that the current I is downwards. So the current is flowing downwards. That means that's conventional current that's flowing downwards. That means that if there were positive charge carriers in the wire, they would be heading downwards. Now, probably the wire has electron charge carriers, which are negative charge carriers, so actually they're flowing in the opposite direction. The electrons would be flowing up. So if we think about current, it's the easiest thing to do here. The current, I, is down, but the electron motion, flow, is actually up. Well, we could apply the right-hand rule to the current. So if I was going to apply the right-hand rule to the current, I'm going to point the palm of my right hand down because the current's going down. I'm going to curl my fingers into the screen because the magnetic field is into the screen, as indicated by the crosses. My thumb is going to point in the direction of the force on the conventional current. And the direction of that force is indicated here is towards the right. So the wire is pushed towards the right, wire is deflected towards the right. If I was perverse, I could think about the electrons. I could think about the electrons moving up the wire. I could have thought about individual electrons moving up the wire. So I could have pointed the palm of my hand in the direction of the velocity of an electron. I could curl my fingers in the direction of the magnetic field. If I do that, the thumb points towards the left. That would be the force on a positive charge carrier towards the left, but my electron that's experiencing this force is negative, so the force on each electron is towards the right. And all those little forces on all those little electrons towards the right accumulate to create this net force on the wire that is also towards the right. So I'm just saying there, you could think about it two different ways. I think it's easiest to think about it as a current as a whole, and use the right-hand rule with currents to figure out the direction of the force. But you could think about it in terms of electrons, individual electrons, the forces on them, but you have to use the right-hand rule remembering the electrons are negative. But either way round, right, you've got to get the same result, that the wire was deflected towards the right. This is the same picture, but now the current conventional current is not flowing down, it's flowing up, which means that the electrons are not flowing up. The electrons which were flowing up are now flowing down. So everything's reversed here. Current was down, it's now up. Electrons were up, they're now down. And because the velocities or the currents are reversed, but the magnetic field didn't change, the force reverses. So if we went through the exercise of the right-hand rule, if you just reverse one of the vectors, like here we're reversing the velocity vector, or we're reversing the current vector, we're reversing the velocity's direction or the current's direction, keeping the magnetic field unchanged, keeping the magnetic field in the same orientation, then the consequence is that the force reverses. So if you flip the direction of the current, you're going to flip the direction of the magnetic force. If you flip the direction of motion of the electrons, you're going to flip the direction of the magnetic force if you're not changing the magnetic field. And so that's what's shown here. We got a deflection now that is towards the left rather than towards the right. I want to look at an example of this, illustration of this, and it's what we call magnetic levitation, right? Magnetic levitation is where you can lift something, or you can support something without physically supporting or physically holding that something. So that's levitation. We can make an object float in the Earth's gravitational field with an additional magnetic field. That's magnetic levitation. And here's a simple example of magnetic levitation where we're going to think about floating a wire in a magnetic field where the magnetic force is supporting the wire rather than using physical support, so cables to support the wire. So this is magnetic levitation. Now you might say, well, this is just some little example you've dreamt up to make a problem involving magnetic forces. It has no application whatsoever, but it does have plenty of real life applications. So there are many trains, the high-speed trains, Japan has them, Korea has them, China has them, that use magnetic levitation for their trains. To get high-speed trains, you don't want trains running on wheels with all the friction and the ball bearings and everything wearing out. So they float their trains, they levitate their trains with magnetic forces from magnetic fields, and they can move frictionless, basically, without the friction of the wheels. So this is a real practical application. We're just going to float a wire, but actually in real life, with real engineers designing it, you can float real trains and go at, I think, up to like 350 miles per hour, some ridiculous speed like that, with a magnetically levitated train. Okay, I've forgotten what I was going to do. In this particular problem, we're going to levitate this metal, this conductor here, in a magnetic field that's providing the levitation against the downward pull of the gravitational field. We're told a few pieces of information, right? We're told the again, this is kind of, we talked about the properties of a charged particle, the charge and the mass. What's the important properties here? Well, we'll discover the important properties here will be the current and the mass per unit length for the rod. So the end result will be something that we work out in terms of the current in the rod and its mass per unit length, rather than charge and mass in the previous examples. Well, here is the mass per unit length. Here's the magnetic field that we're supporting the rod with, and we're asked to figure out what this current is that will perfectly levitate the rod in the magnetic field. So that's our task here. I'll do this on the document camera. But that's not the document camera. Okay. Again, because my anxiety, I've started this problem, I've made a little sketch, and this gets us going. And I've written down the things that we know. Here's the rod that's going to carry the current. That rod, of course, will be pulled downwards by Earth's gravitational attraction, a gravitational force, and I sketched that. Fg is the gravitational force. I've told you how this works. To levitate, we've got to oppose the Earth's gravitational pull by creating an upwards magnetic force that will counteract gravity. And so I've also pictured that with this arrow here. So these two arrows are the downward gravitational force, the upward magnetic force. I've drawn them opposite directions because we need that. I've drawn them equal sizes because we need them to perfectly cancel out and make zero net force. So that the rod literally does levitate and float in air. Okay. So what are we being asked for in this problem? We're being asked for the current. Why are we being asked for the current? Because we need the current to float the rod, right? If the rod's not carrying a current, it's not going to experience a magnetic force, and therefore it's not going to float. The more current, the more magnetic force, and so there's some particular current that will perfectly float the rod, because that particular current will create a magnetic force that perfectly balances the gravitational force. So that's the situation we're going to find. Before I do all that, though, let's just answer the question: what is the direction of the current? Does it go towards the right on this screen, or does the current go towards the left on the screen? This would be the first kind of obvious question. Well, we can use the right-hand rule for that. Again, this is practice in the right-hand rule. It's slightly different because in this case, I know the direction of the. I know the direction of the force. I'm not trying to find the direction of the force. I'm trying to find the direction of the current in this particular case. So we're using our hand in a slightly different way. And so let's just think about that. I want my field, I didn't show the field lines in this picture, they're pointing in towards the screen. So here's the field. So I know my fingers have got to curl in towards the screen, and I know I want an upwards force. So let's try the right-hand rule for the two possibilities. Maybe the current's going towards the left. Let's try it for that, see if we get an upwards force. Maybe it's going towards the right. Let's try that, see if we get an upwards force. So if the current was going towards the left, then I'm going to use my right hand, put my fingers towards the left. I'm going to curl my fingers in towards the screen because that's the direction of the magnetic field. So this is the right hand rule. My thumb is pointing down. That's no good, because that's going to create a downwards magnetic force. That's not going to help support the wire. It must be that the current is towards the right, the other direction, because the current is towards the right and the field is in towards the screen. I'm going to curl my fingers in towards the screen. My thumb is pointing outwards. So we know that the current, we know we need a current. That was the first thing we said, to make a magnetic force. And we know the direction of the current is over here towards the right. So that's important. Okay, now let's find the size. Key idea. Gravitational force, size, equals magnetic force. I'm just thinking about the size now. Let's remember back to the field equations again. We keep meeting these field equations. mg for gravitational force, the property, mass, that feels the force times the field. I, L, B, sine theta for the magnetic force, the property that feels the force, a current in a wire, times the field that carries the force. In this particular case again, if you look at the picture, the current and the field are right angles to one another. Currents in the plane of the paper along the wire, the field's perpendicular to the plane of the paper, so it's 90 degrees is the angle between those two vectors. It's sine of 90 degrees, that's 1. So we actually just got ILB. Oh, this is easy now. I can rearrange for the unknown current. If I rearrange, all I got to do is divide through by L and B, and I get M over L times G over B. I mean, when you stand up here and you're sitting there, when you stand up here, you can't do any basic algebra anymore. There's something about that. Anyway, I've got the solution here, so I was able to look it up, and it's M over L. Current is M over L times G over B. It's an interesting formula. It's a very interesting formula to me because it's got kind of that characteristic of the wire, mass per unit length, M over L, and then it's multiplied by a ratio of two fields, the gravitational field and the magnetic field. Obviously, if we're on Saturn where gravity is bigger, G is bigger, we need a bigger field. If we're on the moon where G is smaller, we need a smaller field. So it makes, we need a smaller current. So it makes sense like that. If we had a bigger magnet, a bigger B, then we'd need a smaller current to put in that field. If we had a weaker magnet, we'd need a bigger current to put in that field. So the formula makes sense. Anyway, enough of that. Let's plug in the numbers. I've got to plug in so this was 0.04 kilograms per meter. So plug that in for M over L. Got to plug in, I never wrote it down, but G was 9.8 meters per second, obviously. I've got to plug in B, which is 3.6 Tesla, so that's the G and the B here. And if you do all that, I got 0.11 amps. 0.11 amps. That's the magic. That's the magic current that floats the rock. So if you're going to build a magnetic train that levitates, then you've got to design for the current that you need to levitate the train. And so we didn't build a train, but we're qualified now to build a train. Okay. Last example. Not the last example. I want to talk about not a straight wire in a magnetic field, but a loop of wire in a magnetic field. We'll think about a rectangular loop of wire, but it actually could be any loop of wire. And we want to think about the forces and the torques that act on this. We just built a levitating train. Now we're going to be engineers again. We're going to build the first electric motor. And obviously electric motor is enormously important to us. And so this particular example here is of immense practical importance. I mentioned earlier on that if you think about the universe or the world from the perspective of energy, everything's about energy transforms one form to another. Energy conversion from one form to another. The Industrial Revolution, 200 years now after the Industrial Revolution, or whenever it was, I don't know. It was really the birth of understanding how to transform and building the technology for transforming energy from one form to another. So a steam engine transforms chemical energy to heat energy, thermal energy, to kinetic energy. This transform of energy, and that, suddenly our world changed. Gasoline engines do a similar thing. They take chemical energy, they turn it into thermal energy, turn it into kinetic energy. This example here, if in this circuit, right, It's got a battery, chemical energy. We're going to turn that, we made a circuit, make electrical energy. We're going to turn it into kinetic energy. We're going to rotate this loop of wire. You can see it rotating in this magnetic field here. So this is an example of magnetism applied to energy conversion. And without the ability to do this, we're basically in the Stone Age, right? In the Stone Age, the only thing we could do, only conversion of energy that we ever did was burn something, which is chemical energy to heat energy, which keeps us warm and maybe cooks our food. But for most of human existence, hundreds of thousands of years of human existence, that's all the only energy conversion we did. And then last 200 years, some tiny slither of human existence, we're lucky enough that we can convert all types of energy into all other types of energy, and we've got a whole brave new world. Anyway, let's solve this problem. We got a square loop here. A square loop of conductors, made it out of 4 straight conductors. A current is flowing around this loop. This loop is immersed in a magnetic field. The magnetic field is from left to right, indicated by these green field lines here. So look at the current. It's traveling across the top arm towards the left, then it travels down the bottom arm, down the left-hand arm here, then it travels towards the right across the bottom arm, and then it travels back up on the right-hand arm here. So it makes a complete loop. This is a current loop, and it's immersed in this magnetic field. This is exactly the problem I'm going to talk about. I've got this one slide here on what are the forces on the loop, and then the next slide, next couple of slides are what is the torque, the turning force on the loop. The force is interesting. The actual answer is that there's no net force on this loop, but there are forces on parts of the loop. So I just wanted to explain that. We said that QVB sine theta meant that if sine theta is 0 or 180 degrees, that's a direction for a particle where there's no force on it in a magnetic field. Same for ILB sine theta. If the current's flowing in the direction of the field lines or opposite the direction of the field lines, there's no magnetic force. Upstairs here and downstairs here, the horizontal arms in this picture, there's no magnetic force on them because the currents are flowing in the direction of the field or opposite the direction of the field. There are forces on this arm here on the left and this arm here on the right. In those two arms, the current is going up or down in the sketch. The field is going to the right in the sketch. So the current and field are at right angles to one another. So you get a force that's just ILB. This arm over here, I called it arm number 1. I labeled its force 1. And this dot means it's coming out of the screen. It's being pushed out of the screen. Got that by right-hand rule. This arm over here, labeled it arm number 2. The force on it is F2. It's into the screen, as indicated by this cross here. Again, right-hand rule. Just pointing the palm of the hand in the direction of the current, curling the fingers in the direction of the field. You get these two directions for the forces here. The strengths are both, I don't know what the N is. Oh, I know what the N is. I made N turns of this loop. I never explained that. I completely forgot about that. This not one loop. One loop, if you build one loop, like my picture to start with, you won't get a very big force. So when you make a motor, right, you're going to make many loops of wire. So N is the number of loops of wire. So this is the field equation, ILB sine theta, times the number of loops. The number of loops of wires, so that's the N here. Anyway, you get these expressions for the forces, but because one's out and one's in, they're equal and opposite. And so they cancel each other out. So actually, the end of this story is that a loop of wire in this uniform magnetic field experiences no force. Parts of it experience a force, but overall experience no force. However, there is a torque on the loop of wire. Now, torque is built out of forces, and there are non-zero forces on parts of the wire, so we can build a torque. And the torque, we can see in this picture, tends to rotate that loop of wire. And because it tends to rotate this loop of wire, is turning that electrical current, that electrical energy that's flowing in the wire, is turning it into rotational kinetic energy. This is how you build an electric motor. So now look at this picture here. It's the same loop of wire in the same field, but I'm looking at it from a different orientation. In the last sketch, I was looking at it from kind of from the side. Now I've got in my helicopter, I'm flying above it and looking down. If I look down, right, here's that left-hand wire. I'm looking down on the left-hand wire that's experiencing a force in one direction here. We already worked that out. And then there was the right-hand wire that experiences the force in the other direction, and I've sketched that here. This loop of wire, I'm going to allow it to rotate about the center, because these two forces, one up, one down, one on the left, one on the right, will create a torque that wants to rotate it about its center. So what we realize from understanding the forces on the wire, although there's no net force, because those forces don't act at the center of the wire, they act on the edges of the wire, they tend to turn the wire, and we can calculate the torque. And if you do the calculation of the torque, so this is where I'm going to go really fast and give you the answer. If you do the calculation of the torque, the wire on the left is going to create a torque, tau1 from R1, F1. Wire on the right is going to calculate contribute a torque. It's tau2 from F2. We've got to add those two torques together. Since those two torques are determined by the two forces, we can write down the equation for the total torque that's due to the two torques that are due to the two forces. That total torque on the loop of wire in the magnetic field is given by this expression here. B is the magnetic field that you're immersed in. Of course it depends on the magnetic field. If you switch that off, it's going to go away. A is the cross-sectional area of the loop, the size of the loop. If you make a bigger loop, you're going to get a bigger torque. Smaller loop, smaller torque. I is the current that you're flowing around the loop. More current, obviously, more torque. And N is the number of turns around the loop. Basically, how many loops you made as you wrap the wire around and round and round. And so this is the expression for the torque. B is the magnetic field that you're immersing the loop in. All the other symbols here are features of the loop. Right? A is a feature of the loop itself. It's its area. I is a feature of the loop. It's its current. N is a feature of the loop. It's the number of turns of the loop. And so these three quantities that are features of the loop, we tend to group together, and we call their product the magnetic dipole moment. And so the torque on a loop in a magnetic field is magnetic dipole moment. We give it the symbol mu times the magnetic field. And so this is the bottom line of this slide. So we found that we can create rotational motion by immersing a loop of wire in a magnetic field. That is how you build an electric motor. I'm going to show you one more. I'm not going to get to the quiz, right? I run out of time. So I'll give everybody credit for the quiz, but I just want to show you the next slide with the one more formula on it. It's this formula here. It's the same formula as the last slide, but the last slide we worked out a special case where the orientation of the field was across the surface of the loop, where there was 90 degrees between the area vector representing the loop and the magnetic field vector representing the magnetic field. If that wasn't 90 degrees, the torque is given by this little formula here, mu b sine theta. That's the one change. Today's class, we looked at some examples, illustrations of